Hello, everyone. I'm Shiqi. I'm working at TikTok at Mountain View office. So today I really would like to share our experience with manager code, optimizing manager code running in client. So client here is like a phone apps. So this is my agenda for today. So the first topic is I'm going to share Android optimization, the tools used in ByteDance. And I would like to focus on more about Redex. So Redex is a tool developed by Facebook. It's an open source tool and developed and maintained by Facebook. And in the past year, we took this tool, we use this tool, and also we develop a few more passes. And today I would like to share two of them. And then the second part is Unity 3D optimization. So Unity 3D is a 3D engine, so which is based on .NET. And so I would like to go through how we do the optimization at the .NET bytecode. Yeah, so Android Dex optimization. So Dex is a very similar bytecode to Java bytecode. It's actually generated after Java bytecode. So when you develop an app, the package size of the app actually is very important. So we would like to make it as small as possible, because for business reason, if the app size is very small, it's very good for attracting more users to increase user adoption rate, and therefore to grow the app. And then so the existing Android package size shrinker tools there are many. So there are a couple. Three of them we think are very popular used in the Android development. One is ProGuard, another is R8, and the last one is Redex. So at ByteDance, so we are currently using ProGuard plus Redex. And again, so Redex is an open source tool. Yeah, and so at ByteDance, we started using Redex about 1 year ago. So then on the average, it helps us to reduce package size on average by like 3.8%. So we enabled 10 passes from 39 passes we explore there, because Redex, it comes with a set of default passes. So we tried 39 of them and enabled 10 of them. So it's not like we can directly to enable all of them at once. Some of them we needed to do some modification. Beyond that, we also developed a couple more passes by ourselves. So Redex, it's like a framework. So you allowed users developer to continue developing more passes on top of this platform. So next, I'm going to share two passes we developed on top of Redex, and the first one is StringBuilderOutliner pass. So StringBuilderOutliner pass is to recognize some string builder pattern, and then try to use like an automatically refactoring mechanism to reduce the size of string concatenation. So, for example, in Kotlin language, you can write just a one line here to basically to do the string concatenation. It's very handy. and it's the compiler, it's actually desugar it to 1, 2, 3, 4, 5 lines to use a string builder to basically to build up this string. So you can see here. So the code size actually is proportional to number of components in this string concatenation. So it's a linear increasing if you have more components try to concatenate them. So then we have like then the bytecode. So you can see this green bytecode is a translation from this string builder code. So you can see we have invoking append for each component here, and then if we can automatically to refactor this code here, so we can actually reduce this 6-line code down to three lines. So you can see here we introduce outline function. It's called outline.o, and it takes all the components here, and then inside of this function it does the string concatenation. So therefore we can reduce the on in terms of code size down to almost O1. So it's not exactly O1, but it's almost O1. So string builder pass, actually Redex does include a very similar pass, string builder outline pass. But actually we tried it initially, and we noticed like the overall size has been increased by a little bit. So so we investigate more. We found out like the reason is the outline function. The outline functions are too specific. For example, for the previous example here, it generates an outline function which is very specific to each component. So in the previous here we have 2 string, one integer. So then Redex will generate. Sorry, this should be 2 strings here and one integer. So for each pattern you discovered, you will generate an outline function very specific. Then each parameter type is exactly each component type. So which means if we do have lots of patterns with all kinds of different types, then then you will generate a lot of these outline function. And therefore, for example, if each function is being used only once, which means it's not going to reduce the code size. Actually, you will increase the code size. So then we did some improvement on top of that. So the improvement of what we did is so we generate outline function. We do not use and each component, each parameter type is more general. So which means like the outline function, and each parameter are typed as object. So which means the pros is so it's obvious because we can generate a fewer outline function, and therefore to reduce the package size. But the cons is like for primitive type, for primitive types in Java, it can, if you want to convert it to an object, we need to do boxing. So we need to do boxing to basically to copy it to heap, then return a pointer, then send this pointer as an object pointer to outline function. So which means for primitive type, we are going to generate. We will remove one append call instruction, but adding two more instruction. One is for boxing, and another is for move the result. So move the result basically to move the result from which is the return of boxing instruction. So which means we cannot trivially convert each string builder pattern to this outline an outline function. Then we need to make a decision for each pattern we discovered. So the decision logic, it turns out, is very simple, because for each reference type we can remove one append call. So that's it. So which means one instruction is reduced. But for a parameter, it's a primitive type, then we will remove one append call, but we add a box instruction and one remove result instruction. So overall, it's like one instruction is added. So basically, so overall, if we count how many reference type and how many primitive type, we only do the replacement if we see more reference types than primitive type. So of course, this solution it has some performance impact by purely purely if we just inspecting this strategy here, because boxing, it will increase, it will cost, it has perf cost, and then calling into another function also has performance cost. So fortunately, after we implemented this strategy, and then we did a end-to-end testing, and no performance regression is noticed. So which means these performance cost, they are very, very insignificant. So our backup plan is, if we notice any performance regression, we will do some profiling to find out like what are a set of methods with high frequency usage. Then we can ignore the auto refactoring in these methods. So the overall profit for this pass is we reduce the package size by 0.3%. So so that's the first pass. Okay, so so now I'm going to share a second pass, which also it is a Redex pass. So, and the goal of this pass is also it tries to reduce the package size. So this pass is called a KtDataClass pass. So Kotlin is a new language. It's used very popular now in Android development. So Kotlin data class, it's a class with some automatically derived members. For example, equal, hash code, toString, component, and copy. So I think it's the equal hash code, toString, copy are very common, and the component n it is used in destructuring declaration. For example, it's kind of like a pattern matching on an object. For example, if we declare a data class person, this person class, it contains two fields, name and age, and then we can write some syntax like this. On the left-hand side, it's tuple-like pattern matching. On the right-hand side, it's the object itself. So if this line is desugared, so it can be transformed into two lines, and then each line it invokes component 1, component 2. Each one corresponds to two different fields. Okay, so what kind of optimization opportunities here do we have? We have two opportunities here. One is replacing this component n by getter. So Kotlin compiler, it generates both this component method as well as a getter. So well, they're very similar. The reason the compiler it generates these two methods is the component method. It's marked as an operator. So an operator like a plus minus assignment, it's marked as an operator. So because this destructuring line here, it is actually an operation on person on this object. So which means it cannot use well at the Kotlin language level. So by the language semantics, this operation, it has to use this destructuring. It's an operation, so it has to use an operator to do this. So a normal getter is not acceptable. But once it compiles, once the Kotlin language is compiled, Kotlin code compiles down to Java bytecode, which means Java bytecode, it does not need to obey all the Kotlin semantics rules. Then at this time, we can actually replace this component by field getter. So in for example here, we have two methods. We can replace this component 1 by this get a. So this is a very easy replacement. So we can basically do the replacement in very easy. So that's the first thing we can do with Kotlin data class because we remove then we can remove the component method, the component operator. So therefore we can save the package size. Second one is toString. So toString is also automatically generated by Kotlin compiler. So it generated this toString implementation. Basically it just generate the printing algorithm for each field for each field, and then it doesn't use any. It's very trivial to generate this. So which means if we have n fields, the compiler will generate n blocks, code blocks, string builder blocks like this, which means it's the code size is also proportional to number of fields. So, well, generated in this pattern, it's it's very efficient. It's very efficient. You just print this one by one. It doesn't use any reflection yeah, it doesn't use any reflection. So it's very efficient. But the overall, it's proportional to the size is proportional to the number of parameters. Okay, so then we try to do this, implement this to string using reflection. So which means we try to get all the fields and then print all the fields in a for loop. And yeah, so we use the refreshing to get all the fields and then print them one by one using a for loop. So which we can reduce the code size down to 0.1. So it's not proportional to the number of fields anymore. And then we created this general toString method, and then in this each toString, we add we only need 3 lines of instruction to basically to invoke this general toString. So which means we can dramatically reduce the toString size. Okay, again, so this strategy, it's not perfect, because using reflection here, it's also, it costs more. The cost is more expensive than just enumerate each field and print them. So there is some performance cost for toString. Okay, so how about this equal and hash code? For equal and hash code, ideally we can apply similar strategy as toString to instead of like enumerate all the fields in equal and hash code. We can also use the reflection strategy, basically to use a for loop to go through each of them. But these two methods, they are used a lot in performance critical code paths. For example, when you inserting an element into a map, right? So you must invoke. It's likely will invoke hash code and equal. So if we using very heavy reflection, you will affect performance a lot. So the package size reduced. So now let's look at like how much package size with these two strategy we can achieve. If we only implement reducing component to n, so we can reduce the package size by 0.07%. So if we combine with the strategy in toString, we can reduce 0.18%. We also tried this toString equal. We also tried to optimize equals in the hash code, even though we didn't eventually use them. So then the overall package size reduction can be 0.34. So yeah, so that's for the last one here. We just try to we would like to see like if we what's the full capacity for the size reduction it can be. So we finally we choose the middle one, the component plus toString strategy. And then fortunately, so even though the toString we use reflection, and we know it's going to be more expensive. Fortunately, we didn't notice the perf regression during end-to-end testing. And I think one reason is because this toString it's more used in debugging situation. For example, you see here, it's just a print class name and a field name equal to the actual value of the field. It's more used in debugging. Yeah, so that's why in actual runtime for an app, I doubt we use any toString methods. Okay, so that's the coding data class pass. So these two passes are additional. We developed on top of Redex, and then both of them has already landed in our app build process, and then these two already helping us to reducing the package size. Okay, so the next topic is Unity app bytecode optimization. So after use of Redex and learned like this bytecode to bytecode transformation to achieve code size optimization. Now we apply this similar idea to Unity apps. Unity is a 3D engine for cross-platform development, and the stack is .NET, open source .NET, which is mono. So developer writing C#, and then Unity engine uses the .NET compiler, compile it to .NET IL code, and then there is another tool. It's called IL2 CPP. It's developed by Unity. It's a translator. It translates .NET IL code to C++ code, and then it uses CLin compile C++ to the target architectures. Okay, so for us, because we want to optimize for Unity apps, the goal is purely for better performance, because for 3D apps, if we can make the code running faster, which means we can target more phones, therefore to acquire more users. So we developed a tool. It's called a ReIL. So ReIL, it's a tool. It's a tool similar to Redex, but it takes .NET IL code in DLL file format, and it does some transformation optimization, and it emits IL code again. So this is it's dynamically loaded by Unity linker. So as an external step, because Unity linker supports plugin. So ReIL is a plugin for Unity linker, and then you process IL with sub-steps. So we architecture the ReIL as a little platform. So our each steps is kind of like a plugin architecture. And then so the main target for this tool is to make the app running faster, so for better performance. Okay, so here is a diagram which I hope it can illustrate the compilation pipeline for Unity apps. So it compiles C# code down to IL, then linker, then this linker. So this linker, it's not a linker in native code in the sense of native code. It's kind of like aggregate all the IL file and then do some processing. It's very similar to LTO, and then do some optimization because you can see everything. Then it generates IL again. Then IL to CPP take all the IL and convert it to C++, and then C++ using CLAN compiled to native binary. So our tool is ReIL. It lives in linker. It's a linker plugin. So it does IL to IL transformation. Okay, and then I would like to share one pass in this ReIL. So it's the devirtualization pass. So devirtualization pass, it's a very common optimization strategy for OO language, because OO language there are different different way we can do dynamic dispatching. So doing dynamic dispatching, if we can do some static, if we can statically try to we can find out what method will be invoked. If we can calculate this at compile time, so basically we can directly call this method instead of leveraging the dynamic dispatching during runtime. Okay, so so you may have a question here is, okay, because all the code eventually compiles down to C++, and we have CLAN here. Why not just let CLAN to do the devirtualization? Because the LLVM is very mature and a very powerful tool. You can do the devirtualization there. Why not just leave it there? And the reason is when IL to CPP convert IL to C++, but it does not actually try to preserve C# class hierarchy in C++. So in other words, it does not generate the C++ code, the class hierarchy, which mapped from C++ code. For example, if I have two classes, a base class and a derived class, derived class inherits from base class in C#. When IL to CPP convert this to C++, it does not preserve this this hierarchy there. So the reason is it's for good reason. So the reason is because in two languages, although they're both OO, but the semantics of this OO class inheritance method overloading, the semantics of these two are not equivalent, which means if we need some semantics, if it does not exist in C++, then this conversion cannot happen at all. So what does IL to CPP do? It actually capture the C# class hierarchy as runtime data. So which means when the app starts, you will populate this class hierarchy when the app starts. And then the dynamic dispatching will be implemented by a runtime library. It will be implemented by a runtime library. So when compile this generator C++, it has to compile with runtime C++ library. So this library can for example, you traverse the C# class hierarchy and try to figure out which method you should actually invoke at runtime. Okay, so that's the reason why we can only implement this at .NET IL code level. So we cannot leave it to later stage, because if we leave it to later stage, we will lose lots of information there, and it will be super hard to do this kind of optimization in later stage. So we implemented this Devirtual pass, and currently we locally calculate. This is an implementation of this pass. So basically, we took a method body, we scanned this body, we converted this method body to SSA, and then if there is any virtual call there, we try to see if we can derive the concrete type of the receiver. If yes, we can. If we are 100% sure that this is the concrete type of the receiver, then we just replace the virtual call to direct call. So we use our benchmark to do the performance the perf testing. So the benchmark shows like there are 8% faster after this pass. So the benchmark is very specific. So we just measure a single measure a single call to a method which without our pass you will at runtime you will invoke dynamic dispatching, but with our pass we will replace it to direct call. So it shows like 8% faster. And the next step for that is we are exploring using we are currently exploring inter-procedure analysis. So we hope we can find a more opportunity once we enable this analysis to discover even more opportunities for the pass like a devirtualization. Okay, so that's everything I would like to present for today. So now the next, if you have any question, I'm also very happy to answer.
Awesome, thank you so much for the presentation. While we're waiting, it seems like there is a question. So are the new Redex passes available as OSS? I guess it's open source.
Okay, so we are planning to open source our passes, and but we want to have it to have more tests and running for a period. Once we know it's stable, it's in good quality, and then we would like to open source it, contribute back to Redex. So currently it is not.
Awesome, thank you. Let's see if there are any more questions. Yes, there is a question. For the 3.9% overall size reduction, how much is from Redex open source and how much is from ByteDance?
I think this is a StringBuilder, the StringBuilder outline pass. So this pass, we wrote a new pass. So the idea is based on the Redex, the original Redex itself, and then but for implementation reason, we just add a new pass aside with the original pass. So I would say this. I don't know. I don't know how I can decompose this 0.36% to the original pass, because we tried the original pass. The original pass is actually increased the package size. So yeah. My answer is I'm not sure.
Thank you. And can you share which 10 Redex passes you found useful?
Sure. The Redex pass found is useful is let me try to. I think in terms of useful, it means like which pass reduce the package size the most. I think one pass is to replace the class name. It helped us to reduce the. I don't remember exactly the number, but I noticed it's somewhere near 1%. Somewhere near 1%. It's like a pass to, because in Java bytecode, so it capture just like the whole string of class name with namespace. Then this Redex pass, reduced the class name to very simple one. For example, a as namespace, then only 3 letters for a class name. I think I can, top of my mind, I think this pass help us reduce very aggressively.
Awesome, thank you. And Wei is asking, do you use D8, R8 aside from Redex to optimize your apps?
Oh, okay, yeah, that's a very good question. So our app didn't start with R8. So currently we are actually investigating like R8 versus ProGuard plus Redex versus R8 plus Redex, and because we have other tools. Actually, they are using ProGuard API to do code modification. So one of our team member, he tried R8 in one of our app, and it found he found like if we want to completely convert it to R8, there are lots of things we need to do, especially for those other code transformation using ProGuard API. It's going to be, it will take longer to do that. So be honest, we don't have any concrete plan to convert to R8, but we realize R8 is the recommended tool, and we are currently trying to figure out what is the best way to migrate to R8.
Awesome, thank you. And I guess since there are no more questions, one last question from me then. I've noticed that in practice, it's pretty hard to find new wins for optimization passes that do not rely on runtime information. That's why, for example, like profile guided optimizations become more and more important, or binary layout optimizations. All of them rely on runtime data. So I wonder, so you mentioned that you use some, I guess, for devirtualization, and I wonder if maybe you use this runtime information for any other passes.
So, so we use runtime information to guide static optimization. For example, another pass we developed for Unity is inlining tool. So inlining function. So basically, we run the game and to profile the game and to list the top frequently invoked method, and then we use this profile to guide our inlining pass. So this actually so far it's pretty good. So it's pretty good because we don't want to aggressively inline everything, because inlining some stuff increase the package size. So we are trying to, it's like doing linear optimization. So we want to find somewhere so it can balance too.
Yeah, finding the sweet spot is always tricky, but that's actually a huge advantage for the profile guided optimization passes, because they have some data, whereas in static context you just have to use some abstract metrics and rely on just wild guesses around whether it's going to be actually beneficial in practice or not. So it's definitely much better. And you also have, I guess, more time. Oh, by the way, speaking of time, I guess the last question, how much extra build time penalty you have because of these extra passes?
So for Redex, I think it's about it's about 15 to 20 minutes additionally. So but this number can be very different because it's on my own machine, and then the build machine actually sorry for that, I didn't monitor this closely because so far it's running. We didn't receive any complaints, so we feel, well, it's good. So we didn't spend much time to look at that. And then for Unity, currently we are it's adding about roughly 10 to 15 more minutes additionally. So, but Unity is not. We are like continuously in development mode. So every week we are adding one new pass. So I don't have any concrete data. So for that, but so far both of them are acceptable. So.
Yeah, that sounds like if you do not monitor this metric, it definitely is not a problem for you, because usually if it's a problem, people will let you know. It's not something that people will just like, oh, whatever, it takes 5 hours.
Yes. Yeah. For Redex, the parallelization is already enabled for each pass, and for Unity, we start from beginning. We from beginning we already using parallelization already. So I think so far so good. So
yeah, hopefully the incremental builds are gonna land as well, so that it's possible to reuse as much as possible pre-processing between the runs, so that you don't have to start from scratch. It's like, for example, in LLVM there are thin LTO pieces that allow you to compute the intermediate state for each of the compile units, so that you don't have to recompute it. If you make a change in just one file, you don't have to recompute it for all the files, and you can reuse it as much as possible. So this is great.
Yep.
Okay, well, thank you so much. On this bright note, we are going to conclude our first day of the event.